Hello, thank you for stopping by. I decided to look at the neural network forward and back propagation and gradient descent issues. I want to visualize that's the key word I want to stress. I want to visualize forward and back propagation in a simple neural network using the IBM Rhapsody model-driven architecture tool to design this network and execute the model and use the gradient descent to minimize the cost. So this is the problem that I want to solve. Given a set of inputs and targets and the weights, can I use the neural network to compute the outputs so that it matches the targets within a predefined error? In other words, to train the model and find the weights, the W's. And the answer is yes. Use the gradient descent algorithm to find the minimum of a function, and then use the forward and back propagation capability of a neural network to minimize that cost or the loss of the neural network. In the forward propagation, we compute the outputs of each neuron in each layer and then compute the cost at the output layer. And the input has just the transferred inputs x as the outputs of that layer. And then in back propagation, we compute the gradients, we update the weights to minimize the cost, and then we iterate again until the cost approaches 0 or that predefined error. The x's and the y's, the targets, are randomly generated within -1 and 1, and the weights are randomly initialized between -0,1 and 0,1. I noticed that an artificial neural network is suitable to an object-oriented design, so I have a layer manager because manages resources. My managers are smart. They maintain the manager ANN model maintains a list of layers and delegates operations to the layer to activate, to compute the gradients, update the weights, and so forth. And then the layer is a neuron manager because the layer manages the neurons. The model does not have a direct access to the neurons, but through each layer. And then the neuron maintains a list of weights that is indexed by the IDs of the previous layer neurons. And this indexing is very important because it constitutes the connection between the current layer and the previous layer. So the size of the weights, the list of weights, is the size of previous layer. It's equal to the neurons in the previous layer. And the neuron encapsulates the operations to activate, where we invoke the activation function, to compute the gradients and update the weights. And then I have a singleton class, the activator, I call it, encapsulates the activation functions and their corresponding derivatives. So the neuron interacts with the activator for those functions and derivatives. So why not use Rational Rhapsody model-driven architecture tool to design this neural network? IBM offers a 90 days free trial for Rhapsody, so that's what I use. And for the compiler, I use the Microsoft Visual Studio 2017 Community Edition. So there is a free lunch in America. What can I say? So we have two major states in this model. in my design, forward propagation states, where we compute the outputs and compute the error at the end, at the output layer, and then back propagation state. To minimize the cost, we use gradient descent and then compute the gradients for the output layer, for the hidden layer, and then update the weights for output and for hidden layer. The two major states, forward propagation and back propagation, they have some substates, and then I call them activation in forward propagation and compute cost, and then the compute gradients and update the weights in back propagation. And also there are some other states, configuration at the startup before the training. I generate the inputs, initialize the weights, and I generate the outputs. Now we can look at a logical view of the UML model, the class diagram. And this is my model. It has, as I said, the layer manager. I call it ANN model. Provides the operations, to allocate the layer, to activate. And so forth, and then it delegates the operations to the layer, maintains a list of layers, and then each layer has a previous layer pointer and a next layer pointer, so I can navigate back and forth during the forward and back propagation. And as I said before, the layer is a neuron manager, maintains a list of neurons, and interacts. The neuron interacts with the activator, as I said, and here is the list of weights, and you see here, this is how I connect. In this connect operation, I allocate the weights based on the connections, which are the number of neurons in the previous layer. Here is the dynamic view. I capture this during the run, but then I will run the actual model. But on startup, we go to idle. We wait until a config event is generated, go to configuration state here, and then over in the configuration we generate a randomly generated X and targets, and then initialize the weights. And then we wait in the configuration for the train event, and from there we go to forward propagation, as I said before, with the substates, active, compute, cost. If we meet the cost, we are successful. Stay there until we do it again. And then if the cost is not low enough, it doesn't reach the limit, we go to back propagation. And this is the default entry, compute gradients, and then update the weights. So we are in configuration. See, after we generate the train event, we activate, we go through all the layers, all the neurons, we compute the cost at the end, and then we go to compute gradients, update the weights, and then go back again until we succeed, we reach this successful state. And now Rational Rhapsody provides a very simple GUI panel interface. This configuration button is associated with this configuration event here. So it's very easy to generate the events. The start train, and here are the generated initialized inputs, the targets, and the white hat, which will be computed every epoch. I display every 5, or maybe I can do it every 1 epoch. Display the target, the computed values. This is my current cost, the limit, and I visualize this water tank. It's the cost. It will go down. I want to visualize it going down until we reach the limit. This is my learning rate. the alpha is used for momentum. So in a scenario, we'll increase the learning rate so that the current cost will not converge, will stay there, will hover at a certain level, and we'll start to increase the alpha, and the cost will go down. But if the alpha is not high enough, it will still not converge. It will hover, the current cost will hover at a lower limit until we increase the alpha to enough value, so we'll converge. In another scenario, we'll set the alpha 0, and then we'll use the step decay. We'll set the learning rate high, and then the learning rate will decay by this amount, 0.05. And also we can use a time decay every 50 or whatever epochs, and these are the formulas that are very well known. Here is the switch where in the computing the gradients we use that's the classic formula, the input sum, the z of the neuron. But some people they use the computed output of that neuron to compute the gradients. And here is the activation. I can set it to different sigmoid, ReLU, but right now the default is 10H. And here is a capture of the successful after 24 epochs. We reached that limit, and you can see that the targets, the computed values meet the targets more or less. In the middle here we have some deltas, but if I set the limit much lower, we can get very accurate results. And these are, so I have total of 4 layers, 1 input, 1 output, 2 hidden layers, and 3 neurons per hidden layer. The first neuron is a bias, and also the input layer has a bias. So I have 11 inputs actually. So let's. I'm going to show some graphics. This is how in forward propagation. This is how I compute the product sum for each neuron, and these are those lists where the index in each list is the ID of the previous neuron. So this is how I compute the output. Also ahead of the schedule is this gradient descent. You see, we compute the cost at the output. We average, if we have more than one outputs, we average over that number of outputs. And here how at the output layer we compute the gradient. We get the error, and then we use the derivative of the activation function of the input sum. But some people use the wide hat to compute the gradient in the derivative. So that's why I had that flag switch in the panel. Here is the hidden layer gradient. I take the running sum, sum of G of the next. I call it the next layer from the point of view of the hidden layer. Compute the sum, and then we multiply the sum with the derivative of the input of that neuron. And then we update the weights, well-known formula, but you can stop the video and look at this. But next slide will show the momentum. So we use the momentum. And here are the actual code in Rhapsody. When I activate a neuron, I pass the previous layer pointer activation type, and then we compute the input sum as we accumulate it here, and then since it's the activator is a singleton, I run and I pass the X, the input sum, and the activation type, and I get the output for each neuron. I compute the output gradients, get the error. Here is the experiment, of using the output to pass to the derivative, but the default is use the input sum, the input of the neuron, and then we multiply the error with the derivative. Compute the hidden gradient. We get the sum here, the gradient sum I call it. Again here the experiment, but the X, the input of the derivative is the input sum. And then multiply that derivative with the sum, gradient sum. Update the weights. Here we use the momentum. See, alpha times the previous weight list before I update the weight list with the delta, and then we add the momentum. If alpha is 0 at the beginning, the momentum is 0, but when we have that scenario where the learning rate is too high, we want to increase the momentum, so we'll increase the alpha, and then the cost will go down. And here we update the weight for each neuron. And here is the activator run function. I have a case statement, and the default is 10H. Now I have, next will be some captures of the output. So when on startup doing the configuration, you see I generate the inputs, the targets, and then I transfer. Layer 0 is the input layer. I transfer. You see the axis matches the output of the input layer, and then layer 1 and layer ID 2, these are the hidden layers. So the first hidden layer has interacts with the input layer. So I have 11 connections. The first in my network architecture, the first neuron in the input layer and in the hidden layers is the bias neuron, the ID 0. So here is the second hidden neuron. Has also 3 neurons, but the weights, it connects to the 3 neurons of the hidden layer. And here is the output layer. It doesn't have a bias neuron, just the outputs, but it's connected to the 3 neurons of the hidden layer. See here. So these are the initial weights generated at startup. And then next I captured, I will doing the run at the end, I capture the successful weights. So here is the I plotted this in Excel. You see layer ID, neuron ID, previous ID, and then they match this if you look careful. So you have the inputs, the first, and then you have the layer ID 1, layer ID 2, and layer ID 3. So you will see this sets of three. Okay. And here is another view of the same neural architecture. These are the successful weights for each neuron. Next, this is see here the learning rate was below 2 and it converged. The cost went down to our predefined close to 0. But here we set the learning rate too high, so it came down, but then it stayed at that level until we increased the alpha, the momentum here. But we didn't increase the alpha enough, so it went down to a low level. We increased it some more, went down until we hit 0.5 alpha. Then we converged here. Now in the next scenario, I set the alpha, the momentum 0, alpha 0, but then we used the decay. So we decreased every 10 or so epochs the learning rate by 0.05, and when we reached 1.9 as before or so, we converged. And here we use the time decay, I believe. So I just label it, learning rate too high, use momentum to minimize the cost. Here learning rate too high, but use step decay, and here we use the time decay. So this is the end of the slideshow. I'll prepare the actual Rational Rhapsody model and run it, so we'll see an actual run. I'm going to pause and then we'll continue. Well, hello again. Now we are in IBM Rational Rhapsody model, and here is the logical view of the system, the software architecture. As we saw in the slides presentation, this is the layer manager, the neuron manager, the layer and the neuron, the weights and the activator. Each class encapsulates the operations, and then the model maintains a list of layers. A layer has a previous and the next layer pointer, and the layer maintains a list of neurons. When it instantiates a neuron, it passes the connections. These are actually the numbers of neurons in the previous layer, so we can instantiate the right amount of weights. So the neuron maintains its weights list and then interacts with an activator. It's a singleton, and as I said before, the singleton encapsulates the operations 10H and the derivative. I keep them in one place, and then when I run, I pass the enumeration type. For example, these are the operations. Let me see the run. See, it's a simple case statement, so I invoke the 10H here as a default. Or then we run the derivative, and we invoke the derivative, corresponding derivative functions based on the activation type. Here is the GUI, the panel. Nothing happens yet, but this is very elegant. You see, we can associate this button with that event, configure event. We can start training, and here are my inputs, randomly generated. The targets randomly generated. I have 10 right now, but we can have 65K, maybe an image. That's for future image recognition. But anyway, I display the computed target outputs, and here is the limit, the current cost. This tank will be full when we start, because I want to visualize it, to see the water going down. Have the learning rate, the momentum, and here are the step decay switches and where I implement these equations. And here is that switch that I said, when we compute the gradients, the default is the Z, the input. But some people use the output of that neuron. And here is the 10H. I can switch here. I like this button. Anyway, so here is the state transition diagram I was telling you about. So let's see. Here the activate the 10H functions. Rhapsody allows me to attach an image, a graphics image, to the state. And here is the cost. If we meet the cost, we are successful. If not, we go back, compute the gradients, and again, this is how you compute the gradients, the output gradients, and then the hidden layer gradients. Compute the sum of the product, and then you multiply that sum with the activation function, again very quickly. And here, this is the code from the update weights. We saw it in the presentation, the momentum here, and then we update the delta, the weight and the delta. So let's give it a try. We start, and here we are in the idle state. See, I just define this state. Stay there until we hit configure here in the panel. We hit configure. We go to the configuration state. See, I configure, and we are in the configuration state. We generated the see, as we saw in the PowerPoint presentation, the inputs, the targets, and here are the layers. I transfer the axis to the output of the input layer. See, they match. The input layer and the hidden layer, they have a biased neuron, the first one, index 0. Layer ID 1 is the first hidden layer, interacts with the previous, right? With the input has 11 inputs, right? So the list, the wait list, it was created accordingly. Layer number 2 interacts with the previous hidden layer, and the previous hidden layer has only 3 neurons, so we have only 3 wait lists in the neuron hidden layer 2. And here is the output layer with the initial weights. So these weights will be updated as we go through the execution. So I configure it. Here are my inputs randomly generated, they match. Here is the target. That's my cost limit. Now let's give it a try. We start, and then we update every 3 epochs. The outputs will be updated. So we start, and then let's go. See, this is what happens. Also, I can set a breakpoint in Visual Studio. See, when I do, let me take it out of the way. Okay, I attached it's very convenient. See, we stopped in the compute gradient here, the compute gradients, and compute the hidden gradients. So you see, we accumulate the product sum, call it the next layer because I look backwards. I go backwards, but I look to the next layer to get the weights. So see, and then let me run to the cursor. So we computed the sum, and then we compute the derivatives, the gradient. So let me continue execution here. At the end, I will display the successful rates, and I will capture the successful weights, and I capture it into a text file. Again, because this cost limit is 5 to the power of minus 6, we'll blink here when we get to the end. So here we reach the target. The cost went down. We are in a successful state. Start. Okay. As you can see, we compute. We go down, but we're gonna stay here because alpha is too high. Let's give it so we can have enough data to graph to 20 epochs, and then I'll increase the alpha to 0.15. Okay, let's see, 0.15. It goes down, but still not good enough. So I want to show you the previous successful run, and these are the weights. It is still going, but I want to show you intermediate results here. So you see, based on my alpha, the cost went down, but still was not, alpha was not high enough. Only when alpha reached 0.5, then it started to go down. So in the end, we'll see the results. And I capture here all of these data, intermediate values. I just got an idea. Let's increase alpha some more. 0.55. I should have done that sooner. Okay, we're done. So let's look at the results. It went up and then it went down here when we increased the alpha, the momentum. Okay, next we'll use the step decay. Here it is, we start the training again, and we see the same behavior. Let's turn on the step decay. So after 10 epochs, we'll see the learning rate go down. Okay, 295 by 0.5. Let's increase it to 0. In the meantime, let's look at, until it converges, let's look at the operations that I implemented. For example, I allocate layers. Here, see, I allocate the input layer, hidden and output layer, and this is the, I delegate, I populate the list, and then the layer allocates the neurons, and then we know how many neurons, and then we populate the neuron list and so forth, and the neuron creates the creates the list, the weights list. And here is the activate in the activation state, just a loop and delegate to the layer, and then the layer delegates to the neuron, tells each neuron, it skips the checks for the hidden layer, and then delegates the activate to the neuron. For example, compute gradients. It just delegates compute gradients to the layer, and then the layer to the neuron. So, and then here we compute the output gradient and then the hidden gradient. So you see the symmetry of operations. So here is we compute the activate first. We compute the sum, and then use the 10H function to compute the output. Compute the output gradient, get the error, and then use the derivative. Run the derivative. Update the weights, then this is the momentum where I compute the momentum based on the previous delta, and then update the weights. So let's see the third run, the step decay here of the learning rate, alpha is 0. So you see we slowly minimizing the cost, but because the limit is so low, we still didn't converge yet to that limit. But I want you to see this. So see, so the rate goes down and we slowly go down. See the difference between the momentum and the decay. So we'll turn on the step decay. The learning rate will go down every 10 epochs. And we succeeded. Let's try and use a combination of alpha too. So start again. Now we go down. Okay, so let's reset this to 3, 0 for now, and decay to 2. Start again. Okay, let's display the results. So here is the output of all the runs. In the end, here I want to show you that we use the time decay and the combination of momentum when we increase the alpha sum. So here we had rate decay, I believe, yes, or let's see, step decay, sorry, and then the time decay plus some alpha. But we can start this process, turn the switch instead of turning it manually. We can monitor the behavior of the cost, and if we see that it doesn't decrease, sequentially or in a certain period of time, then we can turn on this decay or the momentum. But this is for a future project. But I just wanted to show you again the dynamic view, forward and back propagation, and using a simple architecture. Once again, thank you very much for watching.